Welcome to 204B Part 7. Now that we know all the different types of relays and contactors that are available to us and we know about the general construction, we're going to look at the operation of different types as well. Generally speaking, all relays work the same way. An electrical signal is sent to the coil and the coil creates a magnetic field. That magnetic field will pull in the armature, which will either close or open the attached contacts. The contacts will either be normally closed or normally open depending on their de-energized state. The relay also has two different voltage ratings, one for the coil and one for the power circuit. And although they can be the same rating, quite often they are different, and it is important to know what the voltage limitations of your coil and your power circuit are so you do not exceed them. Every relay has a coil and a core. However, the core can be either fixed or movable depending on the usage. Fixed core relays are typically smaller plug-in types, where movable core relays are more for industrial usage. The moving part of the relay, whether it is the core or the contacts, is called the armature, and the purpose of the armature is to change the state of the contacts, so normally open contacts will close and normally closed contacts will open. A relay or a contactor is an electromagnetic switch meant to turn on and off loads. Magnetic contactors are specifically used for turning on and off high current loads. The contactors are being controlled by remote devices like switches and sensors that we call pilot device, and they can be push buttons, thermostats, photocells, limit switches, or even float or pressure switches. The pilot devices can either be manual or automatic, and they will energize the coil, which creates the magnetic field that pulls in the armature. The contacts are isolated from the coil, so circuits at different voltages or current ratings can be switched using the contacts. The magnetic strength of the coil is dependent directly on the current running through it, which in turn varies with the voltage applied to the coil. In order for the coil to have enough magnetic strength to overcome the armature spring, we need to make sure we have enough voltage. This voltage is called the seal-in voltage and is typically about 85% of what the rated voltage is. If we were to graph the voltage levels of a variable transformer feeding voltage to a 120 volt coil, this is the type of graph that we would find. As we increase the voltage going to the coil, there will be a point in time where the armature will pull in and close the contacts. At that exact point in time, that is enough magnetic force applied to the armature to overcome the armature springs, and that is what we call seal in. At that point, we should be at roughly around 85% of what the total rated voltage of the coil is. The other voltage point we need to be aware of is called dropout voltage, and that's how low can the voltage go before that armature releases and the armature springs overcome the magnetic force. When the coil has rated voltage applied and the armature is pulled in, when we reduce the voltage, we slowly reduce that magnetic field as well. By studying the same graph and looking at the dotted line instead of the solid line, we can see that as we reduce our voltage at about 50% of our rated voltage, we'll find that the armature is going to release, and now the springs are going to overcome the magnetic force. By understanding both the pull-in and the drop-out voltage of our relays and contactors, we can always make sure that our systems are operating within that limitation. And it is important to get our voltage to our coil as closely to the rated voltage as we can. Where we can understand how having too little voltage to my coil could cause problems, we can also have problems by applying too much voltage. High voltage across a coil could have two different dangerous effects. First, it could cause the armature to snap into place too quickly, which will damage the internal components of the relay. Or, the high voltage causes a high current, which will cause excessive heat, which will break down the insulation and cause an internal short. The coil voltage should never be more than 110% of the rated voltage. Supplying below rated voltage across the coil can also have two damaging effects. First, the current in the coil is at its peak right before the armature pulls in, so the coil current at this time can be well above the rated values, and if the armature doesn't pull in, then the coil current will stay high and can burn out. Secondly, if the current is just at or just below the pull-in values, the relay may chatter. What this means is that it will drop in and out rapidly, which can cause pitting, carbon buildup, and high resistance at the contacts. The reason the current is so high right before the armature seals in is all about inductance. As we remember from our theory, inductance is increased when my magnetic path is also increased. Inside my contactor, I have an air gap between my core and my armature. And when I eliminate that air gap, I complete my magnetic path, which will increase my impedance, which will also increase my inductive reactance. Since my inductive reactance goes up, my current will go down after the armature seals in. We see the same type of effect happening as we reduce our voltage going to our coil. As my voltage gets through my dropout point, what we'll find is as the armature opens up and I gain that air gap back, it is also reducing my inductive reactance, which will increase the current going through my coil again. So we can see this action between the current and the voltage and whether or not that core is open or closed and the inductive reactance within it. If we are to block the armature, which would not allow it to close at all, what we would find is the current would continue to rise to the point where the coil is going to burn out. We always must be aware that a blocked armature will destroy the coil because of excessive heat happening because the current just keeps rising. You've reached the end of Module 204B. Make sure you are reviewing the module information so you have a solid understanding of what is happening inside the relay and how the relay works. After you've done that, return to Blackboard and you can continue on to 204C.